In this video, I'd like to talk about the Gaussian distribution, which is also called the normal distribution. In case you're already intimately familiar with the Gaussian distribution, it's probably okay to skip this video. But if you're not sure, or if it's been a while since you've worked with the Gaussian distribution or the normal distribution, then please do watch this video all the way to the end. And in the video after this, we'll start applying the Gaussian distribution to developing an anomaly detection algorithm. Let's say x is a real-valued random variable, so x is a real number. If the probability distribution of x is Gaussian with mean mu and variance sigma squared, then we'll write this as x, the random variable, tilde, that's this little tilde, read this, is distributed as and then to denote the Gaussian distribution, we're sometimes going to write script n parentheses mu comma sigma squared. So this script n stands for normal, since Gaussian and normal distribution, they mean the same thing, so synonyms. And a Gaussian distribution is parameterized by two parameters, by a mean parameter, which we denote mu, and a variance parameter, which we denote by sigma squared. If we plot the Gaussian distribution, the Gaussian probability density, it'll look like the bell-shaped curve, which you may have seen before. And so this bell-shaped curve is parameterized by those two parameters, mu and sigma. And the location, or the center of this bell-shaped curve, is the mean mu, and the width of this bell-shaped curve, so roughly that, is the this parameter sigma, is also called one standard deviation. And so this specifies the probability of x taking on different values. So x taking on values, in the middle here is pretty high, since the Gaussian density here is pretty high, whereas x taking on values further and further away will be diminishing in probability. Finally, just for completeness, let me write out the formula for the Gaussian distribution. So the probability of x, and I'll sometimes write this instead of p of x, I'm going to write this as p of x semicolon mu comma sigma squared. And so this denotes that the probability of x is parameterized by the two parameters mu and sigma squared. And the formula for the Gaussian density is this 1 over root 2 pi sigma e to the negative x minus mu squared over 2 sigma squared. So there's no need to memorize this formula. This is just the formula for the bell-shaped curve over here on the left. There's no need to memorize it, and if you ever need to use this, you can always look this up. And so that figure on the left, that is what you get if you take a fixed value of mu and take a fixed value of sigma, and you plot p of x. So this curve here, this is really p of x plotted as a function of x, for a fixed value of mu and of sigma squared. And by the way, sometimes it's easier to think in terms of sigma squared, that's called the variance, and sometimes it's easier to think in terms of sigma. So sigma is called the standard deviation, and it sort of specifies the width of this Gaussian probability density, whereas the square of sigma, so sigma squared, is called the variance. Let's look at some examples of what the Gaussian distribution looks like. If mu equals 0, sigma equals 1, then we have a Gaussian distribution that's centered around 0, because that's mu, and the width of this Gaussian, so that's one standard deviation, is sigma over there. Let's look at some examples of Gaussians. If mu is equal to 0 and sigma equals 1, then that corresponds to a Gaussian distribution that is centered at 0, since mu is 0, and the width of this Gaussian is governed or is controlled by sigma, by that variance parameter sigma. Here's another example. Let's say mu is equal to 0 and sigma is equal to 1/2. So the standard deviation is 1/2, and the variance sigma squared would therefore be the square of 0.5, would be 0.25. And in that case, the Gaussian distribution, the Gaussian probability density, looks like this. Is also centered at 0, but now the width of this is much smaller, because the smaller variance, the width of this Gaussian density is roughly half as wide. But because this is a probability distribution, the area under the curve, that is the shaded area there, that area must integrate to 1. This is a property of probability distributions. And so, this is a much taller Gaussian density because it's half as wide with half the standard deviation, but it's twice as tall. Another example, if sigma is equal to 2, then you get a much fatter, a much wider Gaussian density. And so here, the sigma parameter controls that this Gaussian density has a wider width. And once again, the area under the curve, that is this shaded area, it always integrates to 1. That's a property of probability distributions. And because it's wider, it's also half as tall in order to still integrate to the same thing. And finally, one last example would be if we now change the mu parameter as well, then instead of being centered at 0, we now have a Gaussian distribution that's centered at 3 because this shifts over the entire Gaussian distribution. Next, let's talk about the parameter estimation problem. So what's the parameter estimation problem? Let's say we have a data set of m examples, so x1 through xm, and let's say each of these examples is a row number. Here in the figure, I've plotted an example of a data set. So the horizontal axis is the x-axis, and I have a range of examples of x, and I've just plotted them on this figure here. And the parameter estimation problem is, let's say I suspect that these examples came from a Gaussian distribution. So let's say I suspect that each of my examples, xi, was distributed. That's what this tilde thing means. Let's say I suspect that each of these examples was distributed according to a normal distribution or a Gaussian distribution with some parameter mu and some parameter sigma squared. But I don't know what the values of these parameters are. The problem with parameter estimation is, given my data set, I want to try to figure out, or I want to estimate what are the values of mu and sigma squared. So if you're given a data set like this, it looks like maybe if I estimate what Gaussian distribution the data came from, maybe that might be roughly the Gaussian distribution it came from, with mu being the center of the distribution and sigma, the standard deviation, controlling the width of this Gaussian distribution. Right? It seems like a reasonable fit to the data because it looks like the data has a very high probability of being in the central region, low probability of being further out, even low probability of being further out, and so on. So maybe this is a reasonable estimate of mu and of sigma squared. That is, if it corresponds to a Gaussian distribution that looks like this. So what I'm going to do is just write out the formulas, the standard formulas for estimating the parameters mu and sigma squared. Our estimate, or the way we're going to estimate mu, is going to be just the average of my example. So mu is the mean parameter. Just take my training set, take my m examples and average them, and that gives me the center of this distribution. How about sigma squared? Well, the variance, I'll just write out the standard formula again. I'm going to estimate as sum over 1 through m of xi minus mu squared. And so this mu here is actually the mu that I compute over here using this formula. And what the variance is, or one interpretation of the variance, is that if you look at this term, that's the squared difference between the value I got in my example minus the mean, minus the center, minus the mean of the distribution. And so the variance I'm going to estimate as just the average of the squared differences between my examples minus the mean. And as a side comment, only for those of you that are experts in statistics, if you're an expert in statistics and if you've heard of maximum likelihood estimation, then these parameters, these estimates are actually the maximum likelihood estimates of the parameters mu and sigma squared. But if you haven't heard of that before, don't worry about it. All you need to know is that these are the two standard formulas for how you estimate, for how you try to figure out what are mu and sigma squared given the data set. Finally, one last side comment, again, only for those of you that have maybe taken a statistics class before, but if you've taken a statistics class before, some of you may have seen the formula here where this is m minus 1 instead of m. So this first term becomes 1 over m minus 1 instead of 1 over m. In machine learning, people tend to use this 1 over m formula, but in practice, whether this is 1 over m or 1 over m minus 1, it makes essentially no difference, assuming m is reasonably large, you have like a reasonably large training set size. So just in case you've seen this other version before, in either version works just about equally well, but in machine learning, most people tend to use 1 over m in this formula. And the two versions have slightly different theoretical properties, slightly different mathematical properties, but in practice it really makes very little difference, if any. So hopefully you now have a good sense of what the Gaussian distribution looks like, as well as how to estimate the parameters mu and sigma squared of a Gaussian distribution if you're given a training set, that is, if you're given a set of data that you suspect comes from a Gaussian distribution with unknown parameters mu and sigma squared. In the next video, we'll start to take this and apply it to develop an anomaly detection algorithm.